So now let's do a quick recap of shortest path algorithms, and in particular the role of the priority queue in Dijkstra's algorithm. So just for a little bit of context, so shortest path, we want to go from A to B. And there are efficient algorithms for that. So in my example, I want to go from Hamburg to Munich. This is very different from, for instance, wanting to visit all of the major cities, because then we get the shortest round trip problem or traveling salesperson problem. And that's computationally much more difficult. So it's an NP hard problem. While shortest path, we know efficient algorithms. Most commonly, I would say these three: Dijkstra's algorithm, Bellman-Ford, Floyd-Warshall. So why do I have three algorithms here? So what are the advantages and disadvantages of these algorithms? So the first two, Dijkstra's algorithm and Bellman-Ford, both are single source shortest path algorithms. So I have one source, I'm calculating the shortest path to all other nodes. While Floyd-Warshall is all pairs shortest path. So Floyd-Warshall, as soon as I've run Floyd-Warshall, I have the length of the shortest path from every vertex to every other vertex. That, of course, also comes at a computational cost. So Floyd-Warshall will take more time. Bellman-Ford and Dijkstra, so why do we have two single source shortest path algorithms? That is because Dijkstra's algorithms runs into problems when you have negative weight cycles. Shortest path queries, I mean, I'm not going to say much about that here now, but shortest path queries obviously are extremely relevant anytime we do routing. There, we cannot afford to run such an algorithm because we want to have an answer instantaneously for a very large road network. So this is a very interesting question from a practical perspective. There, one makes heavy use of data structures. And that's not the topic then for today, but an interesting topic to explore. Let's focus on Dijkstra's algorithm. So this is one version of the pseudocode for Dijkstra's algorithm. Let's go through it step by step. First, we unmark all nodes. We initiate the array D, where D is distance to S, and parent is previous node on the shortest path to S, or at least this is what they should be eventually. At the beginning, what we do is we set the distance D for S itself to 0, for every other node to infinity. And also for, in terms of the parents, set the parent of S to itself, and everyone else so far has none as a parent, so it doesn't have a parent yet. So what we then do is we put S into the queue, priority queue, into a priority queue, and get started. And what we do then? So S is now in our priority queue. We take the first node from the priority queue, S in our case, and then for all outgoing edges, so from S I have this edge outgoing, and I have the edge with the 10 outgoing. I relax the edges. Relax the edges means I check whether by using this 2 and whatever it costs to get to S, which is 0, whether I now get a new shortest distance to the node that I reach. This is A in this case. That is the case. So far I couldn't reach A at all, so the distance was infinity. It now gets a distance of 2. D gets a distance of 10. And I put both of those into the priority queue. And I now do the same always with the first node in the priority queue, and they're sorted by distance. A has a 2, so I process A. I have the outgoing edge to B. B therefore gets a 3 plus 2 as a distance, and because it was infinity, I indeed get that 5 there. As a parent, I set A, because I came from there. Now in the priority queue, because 5 is smaller than 10, B is actually the next element that we're going to process. From B, I can go to C. I get a 6 there. B is a parent for C. Now C is the first element. From C, I can reach D. But I can now reach D with a 6 plus 0, which is better than the 10. So I update both parent and the value that I have in D. And in that case, now D, there's nothing left to do, and we're done. So that was Dijkstra's algorithm in short. What's the running time? So for the running time, we will have to look at a few operations here. We always find the first element in our priority queue, and then we're processing it by looking at all outgoing edges, and then possibly updating the distance for the vertex that we have there at the end. That we can do efficiently with a priority queue, and the running time then is, so I mean here essentially every edge might occur once or will occur once. I get a running time of m times, and then possibly I need to update the distance of the to the node at the end. So whatever that operation takes for my priority queue. So the time to decrease a key, and then n times I'm going to take an element out of the priority queue. And I also insert my elements at some point into the priority queue. So I have n times delete min and insert. So what this expression gives us depends on what implementation, so what data structure we use for our priority queue. So priority queues are an abstract data type where you want to be able to do insert, find the minimum, delete the minimum, and decrease key. So, and possibly simply remove and merge. So remove and merge, we're not going to look at, they're also not relevant for Dijkstra's algorithm. Let's focus on the other ones, or more specifically, let's focus on insert, delete minimum, and decrease key. So for binary heaps, all of those are in O of log n time. Actually, if I insert everything at the same time, then I'm building the heap so that I can do slightly more efficient. The operation that I'm not talking about now here, but is kind of the fast one, especially fast one in binary heaps, is a minimum that we can do in O of 1. But for the operations that we actually need, we see that a binary search tree, for instance, would do just as well. What running time does this give us for Dijkstra's algorithm? M times decrease key plus n times t delete min plus t insert. And decrease key, I can just look up as O of log n. All of these are actually log n, O of log n. So this gives me O of n plus n log n, using binary heaps or binary search trees, or balanced binary search trees, I should say. Now, using Fibonacci heaps, so a more advanced data structure that we want to look at later, I can actually do the decrease key faster, at least amortized. And what that means for us, because then delete min, I also have O of log n, amortized constant is, insertion is fast. Anyway, here, then I get an overall running time of O of m plus n log n. So an m could be quadratic in n. So potentially this is much faster than m plus n log n. So at least if my graph is dense. And that's a motivation to look at Fibonacci heaps. Also a good motivation to maybe look at amortized analysis again, because that is then important in the analysis of Fibonacci heaps.